My name is Dmitry Polyakovsky, and I'm excited to be back at RedisConf. Last year, I spoke about using Redis as a cache and also as a queue for background jobs. This year, I want to talk about using it as a database to store rapidly changing data. Also, how to keep the data we store in Redis in sync with other databases used by our application. And last, I will cover different search options for data we have in Redis, including the RediSearch module. First, a quick survey. How many people have used Redis for about a year? 2? 3 plus? It's fantastic. Very experienced audience. Myself, I've used it for about 5 or 6 years. A little bit about me. As I said, my name is Dmitry Polyakovsky. I'm a software developer. I do some Redis consulting in Seattle. And you can follow me on Twitter or read my blog. And I'm also a co-organizer of Seattle Redis Meetup, along with Aaron. Aaron, are you in the audience? Oh, yeah, hey, there's Aaron. So anybody from Seattle, come check us out. We have an event coming up in 2 weeks. Redis Labs is generously providing food. So as I mentioned, I used Redis in a variety of situations. And it was mostly boring data processing stuff. How many people are football fans? Myself, I'm a sort of football fan. Everybody in Seattle has to be a football fan, by the way. My son is a huge football fan. And I wanted to explain to him what the heck it is I do at work. And we built a website together about football, which made us a great partner team because he knows a lot more about football than I am. What it is, it's a very simple leaderboard. And I'm going to refresh. And I'm going to kick off a background process. Actually, it already started. Never mind. So what it's doing is it created 16 concurrent games, all 32 teams in NFL. And for those of you outside US, I'm talking about American football, not what the rest of the world calls football. Anyway, so you have 32 teams in the National Football League. And my randomly generated data has all the teams playing each other at the same time. And every second, a random team scores. So we have a very fast-moving season. And this is our global leaderboard for all the teams. You can see quite a bit of data. You can see the rank. You can see how many points the team has scored. I'm sorry, you don't see it here. You see the combined score. And you can see the percentage. And you can see whether the team is moving up or down. And additionally, I have this other page here where there are 8 separate leaderboards, 1 for each division in the NFL. So the same teams are competing in different competition groups. And you're probably thinking, that is a lot of database queries to gather this data so quickly and refresh this page every 2 seconds. I can assure you, not one piece of data on these web pages came straight from my primary database. I was using Mongo and Redis Cloud, by the way, to host this on Heroku. Instead, all the data you saw was pre-generated in Redis. And behind the scenes of this application, we have very basic models. Are people familiar with MVC structure? Okay. So we have division with many teams. Team will have many games. And games has many scores. And there's also a concept of a score type. So a touchdown is worth 6 points. A field goal is worth 3. Those are the rules of American football. I did not invent them. And additionally, I created leaderboard groups, which is a many-to-many relationship to my teams. And that is how those 2 different pages function. One page has the global leaderboard, where all 32 teams are present. And the other page has 8 separate leaderboards, one with 4 teams in each. But I could have grouped it any way I wanted to. The question you're probably wondering, why should we store data in Redis? What's wrong with Mongo or MySQL? As I said, I'm building a leaderboard. And Redis has data structures that are perfect for leaderboard. And that is, first of those data structures is a sorted set. We have unique members. So if me and my good friend, Aaron, are competing in a leaderboard, he might have 100 points. I might have 120 points. That means I'm number 1 and he's number 2. And if Aaron gets 20 more points, he'll tie with me. And if he gets another 50 points, he'll be ahead. But we are unique members with identical or unique scores, which gives us distinct ranks. And we can easily query Redis Sorted Set and get the data back in this order, ranked by their position. And we could do that and get back those unique members. But what we really want to show on our website is not just a member ID. We want to show a name, logo, description, a lot of metadata. And for that, we could query the primary database, but that is slower and more complex. Instead, we can use Redis hashes to store this metadata in addition to sorted sets. Here's what it looks like in Redis. So we have a sorted set. There's a leaderboard, which is a namespace I defined. Then there's NFL LDBR, which is a unique leaderboard ID. And then there's a sorted set. And what I did is I used the team slugs as a unique member identifiers, which makes it more visual. But in reality, you would probably want to use primary key IDs from your primary database. And this sorted set will automatically tell us that New Orleans Saints are ahead with 22 points, and Patriots, New England Patriots are dead last. Anybody from Boston here? Sorry, randomly generated data. And there's one of these sorted sets per leaderboard. And I use this library in Ruby called Leaderboard, which does some really nice things for me in allowing me to do atomic writes to both the sorted sets and the hashes. And in addition, and here's the hash. So, in addition to, so it creates a key that looks like this, where basically it appends member data to the end of the string to make it a unique key. And then we have the hash keys are unique member IDs from the primary leaderboard sorted set. And hash values are JSON encoded strings. An alternative way to do it would be to actually store each team metadata as a separate hash. But as I said, this library did it this way, and it was pretty easy to encode the stuff as JSON anyway. So here's this hash. And in addition to these sorted sets and hashes provided by the library, I implemented some of my own functionality. If you remember, there were these arrows that showed how the teams are moving up and down. And to track all this information, I created additional sorted sets. So the key in this sorted set is a combination of a team ID, and I called it rank history. That's my own naming convention. And what I'm doing is I'm taking the rank from the primary sorted set and the timestamp, and I'm storing this data. And all I need to do is compare the last one to the previous one, meaning the highest ranking member of this sorted set to the second highest ranking. So the most recent one to the next most recent one. And I can easily determine that in this case, this team, Atlanta Falcons, went from 13 to 14, so they went down in rank. And I actually don't even have to store the entire history of changes, since I only care about the last two. The one limitation with using a sorted set to store this kind of data is that since the since the members here are the rank position in a primary sorted set, I can only store the last time this team was in a particular position. And if I really wanted to build a chart where I could see how the team was moving up and down, this wouldn't work. To do that, what I could is store it as a hash using the time as a key and the position as a value. And then I could extract the data and display it for my users. Are there any questions so far? Well, if there are, just feel free to shout or raise your hand. If I don't see a wave, because I have these very, yes, go ahead.
Why the TTL is -1?
Oh, I'm sorry. So TTL -1, are people familiar with TTL?
Yes.
Basically, yeah. So TTL -1 means never expire. That's just the default Redis thing. Yeah, I mean, you could set expiration on these keys if that is your business case. In fact, in one application, I did it because I only cared to keep this data around for a week. To Redis, this is just a sorted set with a very particular key and some data in it. All the other logic is encapsulated in the library that I'm using and in the additional classes that I wrote. Okay. So when data comes out of my API, it looks like this. I'm combining the sorted set data with the hash data. I'm doing a little bit of formatting. I'm determining whether the team moved up or down in the last rank change, and I'm displaying it. The front end is written in a JavaScript framework called React. To wrap around this leaderboard library, I created a couple of classes. One is called LeaderboardSet, What it expects a score record, and its actual score, like touchdown, a field goal. And from that, I can easily determine which member or team it is for and grab the team slug. And then I can do a calculation of how many points this team has scored so far, which is basically I query the scores table or Mongo collection. I loop through the records. I sum up how many points each one is worth, and I return it to the application. And I use that as the leaderboard score. And then, since I have this many-to-many leaderboard group competition, I loop through all the leaderboard groups that this team is in, and I make the Redis API calls. This leaderboard gem provides really nice functionality for me, and this library has also been ported into Python and JavaScript. And to extract data, I use LeaderboardGet class, which basically just expects the leaderboard ID passed by the front end. And then it grabs data from the sorted set. It grabs data from the hash, merges it together. I do a little bit of extra formatting, and I present it to the front end. And the library supports some nice features, such as ability to paginate through the records. I mean, most of applications we build are not going to have 32 records, 32 teams. We're going to have thousands and thousands of players competing in online games. And you don't want to display all thousands on the UI, so you want to be able to return the first 25, and then use some Redis commands to do a limit and offset pagination. And to Redis, these are just basic, like the commands like zscore or hget. So we've covered one use case for storing data in Redis when it's changing very fast. And this data was pre-generated from data in my primary database. There's another possibility. And we can have the same record, a team, which will have some data attributes which are highly stable, a name, for example, San Francisco 49ers, and I'm going to move tomorrow. And we can store this stable data in our primary DB. And then we can have some attributes which are changing very rapidly. For example, during a football game, the players that are currently playing will change fairly frequently on and off the field. And again, this is just an example. I mean, to anybody who has ever watched a football game, it'll be obvious why you don't need speeds provided by Redis to store this data. But I think it makes a good example. So what you can do is you can define some logic in your application where in the same class model, you have team.name method, which is stored in the primary DB. And that functionality is provided by your ORM, active record, Mongoid, whatever you choose. And then what I did here is implemented a library called Redis objects. And I'm defining this method here called setCurrentlyPlaying. And what this does is it stores the data in Redis. And it builds a Redis key based on a combination of a class name, team, the ID of this particular record, 1, 2, 3, and then what the method name is. And this particular library provides some nice abstractions for me, but you can easily write your own methods like this. All you're doing is you're reading and writing to from a set or a hash or a list in Redis. So anything you can do when you talk to Redis API, you can do here. You can just write your own methods, wrappers on your model. So I can just say team.current, I find a team, New England Patriots, and then I say team.currentlyPlaying, Tom Brady is playing. And in Redis, things look like this. So there's the key based on the methodology I described. And there's a set, and it's just data to Redis. But we can change this data much more rapidly. And we can also have other parts of our application that use the same naming scheme to define a Redis key, reading and writing data to and from Redis. And then our application model can grab it from there. So I can say team.name, team.currentlyPlaying, and the model acts as a traffic cop, fetching data from one database or another. Are there questions about storing data in Redis? OK, well, let's move on. So now that we're storing data in Redis, and this is not cache, which we can easily purge and just regenerate. This is actual data we need to somehow persist or do something with later. We have to worry about how we're going to keep it in sync with the data in our primary database. And this is a similar problem we face when we have two MySQL databases. We have a transactional database and a reporting database. And we have to have some kind of ETL process moving this data back and forth. And we don't want to run this ETL process every hour or every night. We want the data to be as real time as possible. So to move data into Redis, the most common use case in this application is a team actually scores a touchdown or field goal. We fire a callback, And we call that, and we call that LeaderboardSet method, passing a copy of the score record. Are people familiar with callbacks? You know, basically, as you're saving data, your framework does certain things for you automatically. So anyway, so here we pass the copy of the score to LeaderboardSet, and you saw that basic code in this LeaderboardSet class, which figures out which leaderboard records in Redis need to be updated. And we need to do the same after destroying a record. We want to be able to, decrement that leaderboard score. There could be other reasons why we want to move data into Redis. For example, there could be a change in our business logic, also known as we discover a bug in our code. What we want to do is we want to be able to somehow reset the statistics generated in Redis, even though the data in our primary database is recorded accurately. Alternatively, we could have a metadata change. Let's say a team actually moves from San Francisco to somewhere else. And we also could restore a production snapshot to a test environment, and now we want to regenerate data in our test Redis database. And for that, I created a simple LeaderboardReset class, which basically, first, it deletes the data in Redis using this delete leaderboard named method provided by the library that I'm using, which basically deletes the sorted set and deletes the hash. So if you do this, if you go with this solution, you may experience a period of brief, not outage, but there won't be any data in your UI, and you have to be careful in how you do it. Again, based on the applications that I've built, this amount of time was usually less than a minute, which was perfectly fine for my use cases, but your mileage may vary. And then after I delete the data, what I do is I say, oh, I'm deleting data for this leaderboard. Let me loop through all the members of this leaderboard group, and let me simply call LeaderboardSet on the very last score that this team has performed. And alternatively, I could have truly replayed the game for each and every score, but because I'm calculating the total points calculation, this wasn't necessary. So it's a pretty simple ETL process that I built here. Another situation we may have is when we want to take data from Redis and move it into our primary database. So are people fans of TV shows like American Idol? Anybody? I mean, you basically have a situation in those TV shows where in a very brief amount of time, you have to perform a lot of calculations. So 1 million votes could be cast in about a minute by the audience. And you don't want to do 1 million writes to MySQL database in a minute. You could, but it could be a little tricky. And what you instead can do is you can use Redis as a counter to keep incrementing this total points calculation, and when or total votes cast. And when this process is over, then you take those calculations and you simply move that data to your primary database, performing only a few updates. Here's what it looks like in my code. Again, I'm using this Redis objects library, and I define this counter, Redis total points. And I changed my total points method. Before, it would actually query my primary database, loop through the records, calculate the total points. Now, it will either go into Redis or fetch data from this permanent total points field, which is where data move to after the games are over. And it provides a very nice abstraction toward other parts of my application, but it allows me to significantly speed up the calculation in the real time. And the way I call it is I have a callback from the score model. This is when I'm saving a record. I say, hey, total points increment, and I do the calculation of how many points this particular score is worth. In Redis, data looks like this. Basically, the key is built using the same pattern, and now it's just a string to Redis. And you're just performing a Redis increment operation or decrement. So now that we're storing data in Redis, how can we search this data? Has anybody ever tried to build a secondary index in Redis? It's kind of painful. Has anybody ever tried to search for data in Redis without building a secondary index? That's also painful. I've had to do it a few times where I would literally grab all the keys in certain batches and then loop through each and every record, checking does it match a certain pattern. What you can do is you can build a secondary index using sets, where you would create a key that is a combination of the record type, so it's a user, the attribute being indexed, first name, and the value, let's say Dmitry. And then as a members of this set, you would store the IDs of all users with the first name Dmitry. And it's complicated and it wastes a lot of memory. But I decided to try to do it. And I decided to challenge myself to rebuild this NFL website using Redis as the primary database. And I used this library called OM, which stands for Object Hash Mapping. And it has very similar relationship structure to what we see in many ORMs. So I have collection and reference, and then I have attributes, and I can also define index. So I'm using this library called OM. And as I said, I'm defining the relationships instead of the traditional has many and belongs to using the syntax that this library provides. And I'm saying this reference. So team belongs to division. And what this library will do is it's going to build a bunch of Redis keys. So there's a division with ID 1, which is a hash, and that is the actual attributes of that record. And then it'll create a bunch of sets. And this one, as you can see, it's creating a key based on the very similar naming convention that I just described. And the value here, 1, which is the primary key of this division. So if I want to do a search for all my divisions with the names NFC West, it'll first find this set, and then it'll jump to this record and give me the attributes. I mean, in reality, you'd have a lot more records. You'd have a lot more users named Dmitry. Or maybe not Dmitry, but John. And then here I have my teams. So again, here's a team hash for the name Seattle Seahawks or Oakland Raiders. And then there's this index for a team by its name, which I manually set up. And then also, because team belongs to division, this will automatically build an index for the division ID. And again, it's a team index is division ID 1. And if I had division ID 2, it'd be another index for the teams in the division ID 2.
So I have to create this team hashes for you recently.
So yeah, so the nice thing about the library is that it created all these data structures for me. All I had to do from my application code is say team.create name Oakland Raiders, so division.create AFC East, and then team.update division ID 1. So yeah, so the nice thing about this library is that it abstracts all this and creates a lot of keys. But if you don't have a library in your language, it is quite a pain in the butt. And it's also, as you can see, a lot of keys here. And all this stuff has to be stored in RAM. And even think about a key like this. Look at the length of the key and look at the actual value. I mean, think about how much RAM this is going to use. If I have only one user with the name Dmitry and only one user with the name Mary and 1 million users with the name John, I have to create 3 separate indexes right there. Any questions? Yes, go ahead.
So how do you keep consistency between the sets and the data? So
if you don't have a library, very painfully. So I am not recommending this solution for a serious production application. I'm simply using it to show what it takes to build secondary indexes with sets. But the nice thing about this is you can search for data. It has to be exact match. I am looking for Seattle Seahawks. I can't search for a team with a name like Seattle, which you can do in a SQL database. And in my code, I'm sorry, it's a little formatting is a little off. But basically, I can do a query like division 1 that basically will find division with ID 1. And then I can say division.find by name. Again, it'll use the sorted set to find, I'm sorry, not sorted set, set. It'll use a set for this particular index. It'll get the ID for the teams that are in that index, and then it'll return me the data. Again, library abstracts all of it for me. But it's still painful, and it's still not a situation where I would not want to use it to model like a very relational data structure with dozens of tables. This would just not be very feasible in OM and Redis with Redis as a backend. But
Library, it would be hard to do things like engrams.
I'm sorry, say it again?
Even in this library, I guess it would be hard to do things like engrams.
Absolutely. Yeah. You can't do a join with this design. You have to do a lot of application joins where you're querying users, and then you're querying articles, and then you're querying comments, all application level. I mean, it's going to be really fast because Redis will return data to you fast, but still a lot of work. And then if you want to merge the data, for example, you want to see the user names and article titles and the body of the comment. You have to do all of that application side. Okay, but again, you can do something. So if you have like a application with very few models and you want to use Redis as a primary data store, this is one way to do it. I've done it just like on a few prototypes. I've never actually deployed a serious production application like this. This is meant as a pure demonstration of how to do indexes with sets. So that's Division 1 teams. Again, in our code, it's pretty similar to any other ORM. And if I want to search for a team, again, I can search for a team by division ID, and then I find it, and then I can get the data. It looks kind of like this. Are there any other questions about secondary indexes? OK, so that brings me to the RediSearch part. So RediSearch modules, have people tried it? Are people familiar with modules? They were announced last year at RedisConf 2016. There were a lot more talks this year. Very interesting functionality. Soon it's going to be officially supported. But right now, you have to basically clone the repo, compile the code, and in your RedisConf, you have to load it using this command. And you get a lot of other commands. With RediSearch module, you get commands like, and basically there are some libraries for Ruby that I've created a library, and it's particularly designed for integration with Ruby and Rails. But Redis Labs has several libraries. There's one for Python and one for Java. And if you go to the website for RediSearch module, there are a few other community projects. So once you load RediSearch module, you have certain additional commands available to you in addition to get, set. You have this ft create. And what I'm doing here is I'm creating an index with the name team, and I'm defining a schema for that index. So I'm just simply saying I'm going to sort index only name, and it's going to be text index. I will talk more about numeric indexes shortly. And then I can add individual documents to that index. And what I'm doing in my library, I'm creating a naming scheme using a global ID, which is like a URI for records. And it basically takes the model name, team, user, article, and the individual record ID and combines the two to create a truly global ID for a record across your entire application. And that's basically what I just did in my application library, because I was really trying to target simplifying integrating with RediSearch from a Rails application that has maybe a MySQL or Mongo backend as a primary database. And then once you created this index and added a document to it, you can now do a search. So I'm searching an index team for keyword Seattle. And data will come back like this from RediSearch. The very first number will be the number of records that match this search criteria. Then we'll have the unique document ID. And then we'll have this arrays of key value, kind of like key value pairs, but basically the attribute and the value. So in this case, it's name, Seattle Seahawks. If you were indexing users, you could have first name and last name and email, and then you can search for any of those attributes. So you could do a search for like all the users with Gmail addresses. And the RediSearch module will parse the email as it's indexing, grab the Gmail, and create it as one of the keywords for the inverted index. Go ahead.
Like, would this work with pipelining? So if I wanted more information, just like if I want to resolve the unique ID for sales Seahawks to other metadata like the logo.
So I need to integrate pipelining into my library because I haven't done a lot of performance optimization. But I think you probably could. I actually would like to ask Itamar at a session coming up where he talks about deploying RediSearch at scale, about how to do it. I admit, so again, full confession, I've done it on several personal projects because I think it's an awesome technology, and that's one of the challenges I've had with Redis is an ability to search by anything other than key. But I'm not brave enough to deploy unstable Redis for, and compile this module myself and have to run my own EC2 instances on a real production application where my employer might get upset if something goes wrong. But it's a really interesting technology, and once it launches officially, and once Redis Labs or other Redis hosting providers support it, so it's like one click in the dashboard console, I'm definitely going to try it on real applications. So anyway, so in
When I search for a partial name, like SEA, for example,
I couldn't hear you.
the previous page you have to search for Seattle.
Yeah.
So for Seattle, can I search for SEA, for example?
I'll show you later what kind of keywords it creates. Yeah, it does a lot of intelligent stemming. And I'm actually thinking of adding some more functionality into my library about adding like stop words. So, but, and, if, because you don't want to index those usually. But yeah, I've been actually emailing with the module author, Dmitry, who's one of the Redis Labs engineers, and he's adding a lot of really cool stuff. But yeah, I worked in internet advertising, and I can definitely see use cases for where you want to have a lot of either loose or exact search options. And the Redis search module has a lot of options where you can say how you want the search to be performed. It's like a query language. But anyway. OK, so when you say index a document or add document to index in Redis search, by default, it will actually save it as a Redis hash. You can pass a no save parameter, in which case it'll only store the indexes in Redis, and then you'll have to go to your other data store for the actual content of those documents. But hashes look like hashes. Again, there's my global ID that I passed as a unique ID for this document, and there's a name, names. Additionally, RediSearch modules create several custom data types. So one of those data types is this FT index. It'll create it for every index, so for team, for division, for user. And then it'll create these inverted indexes. So, and this is where those keywords are indexed. So Seattle is a keyword. So it'll use this key to find when you search for Seattle, and then it'll find the appropriate index and return you the document data. But here's like division NFC. Like one actually feature I want to add in my library is a minimum keyword length to index. So if I don't want very short keywords indexed, I can choose to exclude them. In code, it looks like this. So you would include this Ruby module, not RediSearch module. And then you call this method called RediSearch schema, which will create an index. So here I'm creating index on a team for its name, which is a text index. And I'm creating a numeric index for the size, size of the team, number of players. And now in my Ruby code, I can do calls to like ft create, and I use the pattern of ft underscore instead of ft dot create, and ft add and other method. I mirrored the RediSearch module methods, but I added a few additional methods. So for example, I added this ft add all, which basically is it's a class level method, so it'll loop through all the teams in a teams table and index all of those records, because RediSearch module is really designed around documents. You can have a bunch of text files you want to feed through it. And I was trying to simplify integration with application where I have some kind of a database with tables and columns. And then I can say ft search keyword, and I say Seattle, and the data comes back in the same structure as directly from Redis CLI. But I also added a method called ft search format, which will return an array of hashes, which is a common pattern in many ORMs. And what I can do then is I can loop through this array and display the data in my UI for my users. And I can also add this numeric filter that I briefly touched on. So what if I only want to know all the teams that match keyword Denver but have between 40 and 50 players in there? So what I do is I search and I specify size and min and max value. And in the Ruby code, I would specify it like this as a filter. And the data comes back the same as before, only with additional filtering. But to make this numeric index work, there's now yet another key in Redis, this numeric index data type. That is a custom data type to RediSearch module. And I actually discovered an interesting problem kind of halfway through this project. I realized that I'm using Redis as the primary database, so I'm already storing all the attributes in Redis as hashes using this OM library. And then, since I was saying index these documents and save the data, the RediSearch module was creating additional hashes to store the same data. So that made me read the docs again for RediSearch, and I found this other method called ft add hash, which is really useful for when you already have data in Redis. You don't want to pass it a separate record, separate document. You simply want to say to RediSearch, go into this, grab this stuff from this hash, and apply it to this index. And it's just ft add hash. And in my library, I have ft underscore add hash, and you have to pass it the unique Redis key where this data is stored. Any questions? Okay. Another useful feature is pagination. I mean, here we have only 32 teams. But in a real-world application, I could see this being deployed to something like users table, where we'll have millions of users and or millions of articles. And we want to be able to search through all of them, but we obviously don't want to return thousands of matching results all at once. So the very first attribute in that results is the number of matching records. And by default, RediSearch will actually return to you the first 10. And what you do is you do simply paginate. And I added this ftsearch count method in my library to get just that very first number. And then you loop through it and you say, give me this next 10 and the next 10 and so on. But it's the same search underneath. And yet another cool feature that I want to cover is auto-completion. Let's imagine that, again, we're indexing all the users in our system. So we build the index to be able to search the users. But then we want to have auto-completion, so as people type first name, they type DMI, and we automatically make a suggestion. Hey, maybe you're looking for Dmitry. So for that, you have to create another type of index in RediSearch using this sug-add or sug-get command to extract data. There's also sug-del to delete records. And what it is, it's an index not on the entire document, but on a particular string. Or in my case, it's on a particular attribute of a model. So I can say, hey, I want to create RediSearch indexes on all the users. But I also want to be able to have auto-completion on the first name. So I'm going to go through all the first names and add them to this dictionary for auto-completion. And RediSearch will create yet another type of key using the team attribute combination, and then it's try type of index. So now if I say, hey, in my code, I can say ft-sug-add team attribute name. And then I also added another method to add all first names or all team names to this auto-completion dictionary. And now I can search, hey, give me all the teams that begin with letter S. So that'll give me Seattle Seahawks. And then I can do a search and retract and extract and retrieve all data about Seattle Seahawks that I have indexed. Perhaps I also have the history of the team or the owner name and other things. Or if we were indexing users, I would say, hey, give me all the users whose names begin with D. So give me Dmitry and Donald and Daisy. And then I'll say, oh, I'm searching for all the Donalds in the system. So I'd select Donald. That would fire another search request to the other indexes. And that will give me all the documents that have the string Donald in them, probably the first name. Some benchmarks. So obviously, storing all these secondary indexes takes up a fair amount of space. Actually, not secondary indexes, RediSearch indexes, I should be more correct. I took a file with like 10,000 users, first names, last names, emails, and it went about 4x in size once I saved the data to RDB. But it was really fast. And it created about 22,000 keys for 10,000 users. So all those additional keywords add up. And then went to 1 million and created about 1.5 million keys. Again, it has to do with the data I was using. Again, randomly generated usernames. Obviously, there were some. It was reusing the same first names, last names, and so on. And it was about 200 megs of data. And once I went to 10 million users, it actually took a long time, about 60 minutes to index them. But I think the problem is in my library because I've been in touch with a module author, and he says that his benchmarks were much faster. But it worked great. I mean, search was like near instantaneous. I could search through anything I wanted. And it was, like I said, really powerful to have full text search, to be able to do all kinds of matching, either exact or more loose match, and to have it all in Redis, and to have it so fast. Are there questions about RediSearch? Don't be shy.
You mentioned pagination, that you are actually moving to the records.
Can you repeat it louder?
Pagination, you're grouping to the records.
Yes, I'm making multiple requests, and I'm specifying a limit and offset. So I'm saying,
So I'm going to get the last page. I'm going to make n-1 request.
I think, well, yeah, you can always make you can always keep requesting the last records. But yes, you can control the number of records per request. I think that's configurable up to a limit. But yes, you have to make multiple requests. So if you have 1,000 users with the first name Dmitry, you can say, give me the first 100 or the first 50, and then make appropriate number of. Yeah, you're right, it is n+1 request, but it's the same problem as in any pagination. I mean, you can request a whole bunch at once. I think there is a limit to how much this library will return the max. Yes?
You mentioned some indexing times in there, the index, but RedisSearch indexing for a website which is continuously used is incremental, right? I mean, you don't have to spend, it doesn't reindex everything.
No, absolutely not, exactly. And in fact, that's one of the features I want to implement in my libraries that's like callbacks, that when a record is saved, it'll automatically index the data.
So, also, I mean, your whole talk was around the index of, you're saying that with RedisSearch, we can now kind of replace relational DBs with Redis.
Well, not quite. I mean, you still don't have relationships. You still can't do a join. I mean, you can do atomic commits, aka transactions, but you can't really model relationships. You can't go from users to articles to comments, or from divisions to teams to scores.
I see. So in this app, I mean, you might not be using relational stuff in this app, but it's still recommended to have just for relational stuff.
Yeah, I'm using Mongo, but you could use a relational database as your primary DB. So you could, I mean, what I say as a potential use case, you have a relational database for an existing website, and then you want to implement Redis for caching, or for background jobs, or for like some of these sorted sets that I described. And then, oh, wouldn't it be cool if we could do a full text search? Well, you can do that against, it's kind of hard to do that against SQL databases, or so instead of setting up Elasticsearch, you could do this.
So I'm not familiar with Mongo, but does Mongo do full text search?
You can do some stuff in Mongo with a full text search, yeah.
Have you done some comparison between Mongo?
So in another website I built, actually, what we ended up doing is we ended up doing Mongo with a Ruby library to do full text search for certain keywords. And the library would take those keywords and it would store them as an array on each Mongo record. So you'd have like a team, and you would take the name of the team and you'd break up those keywords. So there would be additional attributes called keywords. So the search would first go, because again, we haven't deployed it in production because it's not yet generally available. So that code, what it would do is if it was requesting data from the leaderboard, it would say, hey, give me the top 25 ranked members of this leaderboard. But if a user typed search, it would query the primary database for that keyword, whatever they typed, get the IDs of the Mongo records which match that search, and then go to Redis and say, okay, give me data from the leaderboard, but give it to me for these members. So it was a little bit more complex, and given our scale, performance was not a problem, but it would have been cooler and faster and simpler to do something like this. Yes?
Is autocomplete stored and managed independently of the search index?
Autocomplete is a separate index field, yeah. So you can have, let's say, teams where you're going to index the documents and all the keywords in those. And then separately from that, you can build an autocomplete on a particular team attribute.
Okay. So if we're primarily using Elasticsearch right now, could we still leverage autocomplete out of the box without having to do anything else?
So you're saying, could you do autocomplete search, autocomplete query against this Redis index for this autocomplete dictionary, and then say, oh, I got back some strings, because again, all you get back is the strings, so like first names, and then say, oh, you type for DM, therefore you're looking, and then you selected Dmitry, and then do a query against a different data store. I don't see why not.
Okay, so it doesn't, got it.
You'd have to do it all application side, obviously. Any more questions?
So I saw you could filter by certain fields. Is it possible to search and rank by multiple fields and then have certain fields way more than others?
Yes, I didn't talk about that, and I have limited support in my library for this, but there's a way to assign different weights. So you can have like name, description with different weights. I recommend Itamar's talk, which is starting at 3 o'clock, where he's going to go more in depth into that. Well, thank you very much. I hope you enjoyed it. Oh yeah, there's my final slide. Redis is a powerful tool, but with great power comes great responsibility. And that's actually Voltaire, not Uncle Ben. And oh yeah, and here are the links to all the technologies, libraries I mentioned.